Good day, class. In this lesson, we will learn the basic tenets for graphing sine, cosine, and tangent functions. Before you attempt to graph the function, a trigonometric function, you want to be thoughtful about how that equation lays out. Notice how a sine function can be written in this format that you see at the top. We see f of x equals, so we know we're dealing with the function when one thing depends on another. Our input depends on, or our output depends on our input, and this is equal to a, or some number you'll find out that a is going to be, times the sine of this quantity. And this quantity all shapes up to represent what ends up being an angle measure. And so we have inside that quantity an omega. I'm referring to this one as omega x, and so there's our input, that x, and then minus theta. There's an angle measure, and then plus a constant. And so think about carefully, just like we did our shifting with with linear functions, quadratic functions. When we shift left, right, there is some action on that, usually a variable x. There's an action on an input, and so we want to think carefully about how that can lend itself here in the same world of graphing trigonometric functions. And then same thing with shifting up and down, that plus c. We're talking about shifting up and down, plus some constant value. We're shifting up or down there. Recall also with linear and quadratic functions, for example, that shifting left, right, if we're performing a plus some number on the variable x, we end up shifting to the left, and a minus some number, we end up shifting to the right. So keep that in mind, how it sort of works counterintuitively there. So we'll play with that and sort of consider it here. And then you also need to not only be considerate of the way the equation looks, or is shaped, if you will, but also the way the graph looks, the standard y equals sine of x before any shifting up, down, left, right, narrowing, stretching, reflecting over any axes. So this is y equals sine of x. So let's talk about this for a minute. Here we have passing through 0, and I really want you to get this. Just really zoom in on one cycle of sine. This is how sine behaves. We start at 0 for an input, and we get out of 1 for, and we get out of 0 for an output when we use the angle measure 0. Also, when we use the angle measure pi for sine of pi, we end up getting out a y measure of 0. But if you substitute pi over 2 into this function, sine of pi over 2, you're going to end up with a value of 1. And see, this is how sine behaves. And if you substitute 3 pi over 2, which 3 pi over 2 is halfway between pi and 2 pi, then you're going to get out a -1 for your output for your y value. So with that, and then it starts all over. The function, the curve, it's cyclical, so it starts all over. And I'm abbreviating here quite a bit. This is definitely intended for prior knowledge. This particular instructional video is considering that there is a lot of prior knowledge here, so there may be a different instructional video for anyone listening who may not have so much prior knowledge. So here we're looking at that one cycle, one curve of the sine function. And so it starts all over, so we need to be thoughtful about this thing starting at 0, ending at 2 pi on the x-axis, and having an amplitude, which we learned to call it, of a of 1. So we're going up to a maximum of +1 and down to a minimum of -1. And we see that happen. We're dealing with the unit circle. By now you've dealt with the unit circle quite a bit, so you should be familiar. And so we're thinking about that behavior. Cosine function is a little bit different. Notice how at 0 we substitute 0 for cosine, or cosine of 0, we get an output of 1. The cosine of 0 is 1, and then the cosine of pi over 2 is 0. And so we're thinking about this behavior, and it creates this sort of curve, almost like a cup or something. between 0 and 2 pi, and then it starts all over again. And so we notice how we sort of look forward to that cosine curve and when we're getting up to 1 down to -1, and for which angles that's going to occur. And so last but not least, we're dealing with the tangent. So notice how the tangent is a little different. Notice how the tangent, we see asymptotes all over the place. We are passing through 0, 0, 0. We're passing through that origin, and notice how we've got those asymptotes at -pi/2 and +pi/2, and then how those asymptotes sort of reach out. And we'll discuss that a little bit in our last example. But notice how we have here those asymptotes. Super important. We don't have an amplitude here, so we continue to go up to infinity, positive infinity, and down to negative infinity along that asymptote, getting closer and closer to that asymptote. So we see those in the tangent function, and we want to be thoughtful about it, and also want to be thoughtful about how we're passing through 0, but we're also passing through -pi and +pi, which means tangent has just y equals tangent of x has a period of pi instead of 2 pi. So we'll talk about that in a little bit. Keep that in mind, that behavior, what's happening on the 3 different functions, sine, cosine, tangent. Now notice here we have y equals sine of x. So nothing has happened, no shifting has happened. Take a look at y equals 2 times the sine of x. Notice the amplitude has changed. Now I'm taller on either side of that x-axis. I go up to 2 and I go down to -2. So this describes the amplitude, which is where is always a distance, really. So we're talking about an absolute value. And notice what happens if I take that same 2 sine of x and I subtract 1 from that entire quantity. I'm dropping down, I'm shifting down 1 unit. So I got the same graph, I just shifted it down 1 unit. So you want to be thinking all the time about how this appears and how these behaviors appear. So you can kind of glance at the amplitude and the also the shifting up and down, that vertical shifting. You can eyeball it and call it what it is. But regarding if you want to shift any other way, you probably need formulas. So formulas come into play. Let's take a look at this example. Here we have y equals 2 times sine of this quantity, x plus pi/4 minus 1. So now I'm like, okay. We can see in the blue sine, y equals sine of x before any shifting has happened. The red is our new graph. So a lot of things have changed. So instead of trying to guess, we really need to use our formulas. The formula is to find the amplitude. That one, again, you can often eyeball it, but the amplitude is the absolute value of a, because we're talking about a distance. I am abbreviating here, so there's some things that we will maybe talk about in a face-to-face classroom or in a different instructional video, but here they're assuming we really thoroughly understand what the amplitude describes. The period, we're talking about 2 pi over omega. This is described as 2 pi over omega, and then the phase shift is described as theta over omega. So let's play those out. I'm just going to substitute here, absolute value of 2. Here, 2 pi is the period of any sine function, but I want to divide that by my omega, because that omega is going to impact how this thing stretches or narrows. And so I'll divide by 1 in this case, and it just happened that there is no stretching or narrowing. And then, so my period is still 2 pi. Phase shift, in this case, is theta divided by omega. My theta happens to be pi over 4, and my omega is 1. And so I calculate that, and I discover I'm shifting. This is my horizontal shift, my shift left or right. So notice in my original function, 2 times the sine of the quantity x plus pi over 4 minus 1 means that I'm going to be shifting left. So my phase shift is actually negative pi over 4. So make sure you handle that appropriately. And then when you've done that, you can actually see from the original blue sketch to the red sketch that you have stretched. You've gotten taller, gone up from 2 units. You shifted. Your amplitude has gone from a height of 1 on either side of the x-axis to a height of 2 on either side of the x-axis, or length, I should say. Your the period has stayed the same. and we have shifted left pi over 4 steps, and then we have shifted down 1 step. Please feel free to pause this video if you want to double check that and make sure all that has happened. And then you want to be thoughtful. Where does this thing start? Now, it normally started, the curve originally started at pi over at 0, but now it's shifted back to pi over 4, negative pi over 4. So now we're back to negative pi over 4, and then we go out 2 pi units. So where we're starting on our curve is a little different here than where we would have in the first place. In this example, we're looking at the same business, but we're talking about the cosine. So we play all that out. Our amplitude, period, phase shift. We're dealing with those tools. We're using our tools to deal with those elements of the graph. Amplitude, pretty easy. Period. Remember, a cosine goes from 2 pi to 0 to 2 pi. But in this case, we got some shrinking. So we're going from 0 to pi now because our omega in front, which is the number in front of that x, is 2. So we divide 2 pi by our 2, and we end up with us getting skinnier. So now we're talking about a period of pi. So we're going from 0 to 2 pi. Remember, the standard graph of cosine here in this example is the blue graph, and the new graph is the red graph in this particular equation. So in this particular example, and so our phase shift, are we sliding left or right? We're not in this case. Nothing is happening to that 2x. There's no action on that added or subtracted, but we are shifting up a 3rd unit, so we should see that happen as well. And so we kind of notice, even though our period gets shorter, our amplitude gets smaller, we shift up 1/3 unit. And so all that said, we end up with the graph that we see here. Also notice that this thing reflects over the x-axis. How do I know that? We have a negative amplitude or a negative coefficient of that cosine. So this one is going to reflect over the x-axis, almost kind of upside down if you think about it in that regard. Here we're looking at the tangent graph, slightly different. So there are a few different things that you want to consider, because tangent, it relies on sine and cosine, sine over cosine. So really what we want to look at here is the period, the phase shift. Notice how the period for tangent is shorter. It's pi divided by omega, or the absolute value of omega. So we're really talking about a period of pi here. And then the phase shift, in this example, we have a period of pi, and then, so nothing changes from the standard tangent. And then the phase shift is pi. Notice how we're given a theta of pi and an omega of 1. We substitute, we discover, oh, this thing is shifting pi units. How do we know it's shifting? Where is it shifting? It's shifting left, pi units. And so we should expect that to happen in our phase shift. And then we have asymptotes. Asymptotes is the kicker here. We need to know, where is this thing going to never touch? And so I need to calculate my asymptotes, and I'm going to use this formula because the standard tangent graph goes from negative pi over 2 to positive pi over 2, or it has asymptotes at that location. So if I can observe my shifting, which is my omega x minus theta, in relationship to those original asymptotes, then I can find out what are the asymptotes for my new function. And so I'll do that. In this case, I'm looking at x minus pi I'm looking at my compound inequality in this regard. And so I'll solve that. Remember, solving your compound inequality, you just do the same thing to all 3 sections of that equation. In this case, I'm going to add, of that inequality, in this case, I'm going to add pi to all 3 sections. And I end up with negative pi over 2 plus pi on the left, and pi over 2 plus pi on the right. So really my asymptotes are now here. And then notice how this works out. I have an asymptote here at pi over 2 and at 3 pi over 2. No surprise. Where are my other asymptotes though? I can just keep adding pi's. Notice how if I add another pi, because that's my period, I'll go on to a next asymptote at 5 pi over 2. And then if I want to add another pi, I can. And I go on to a next asymptote at 7 pi over 2. If I want to add another pi, I can. I'll go on to a next asymptote at negative pi over 2. If I want to. In this case, I'm going back. So I'm at pi over 2. I'm subtracting a pi. So notice how I end up at negative pi over 2. And those will be my asymptotes down there. So looking for my asymptotes is the kicker here. How do I find them? Pause this screen if you need to. Otherwise, we're done. Let me know if you have questions.